Hi everyone. So today we're going to be talking about maximum likelihood estimation and specifically when we're working with a continuous distribution. So before we go through an example, in general, when we work with MLE, we start with a likelihood function, which is L of theta, which is the product of our density function. Then our goal is to maximize this function by taking the derivative, but to make it a little bit easier, we're going to take the natural log of the likelihood function to get our log likelihood function in order to change the product to a sum. And then lastly, we will derive this function and set it equal to 0 in order to get our MLE estimator. So let's go through an example with this process in mind, specifically for the Pareto distribution, which we have some information listed here for. So for our example, it says that given the data set below, we want to estimate the value of alpha for a Pareto distribution with theta equal to 700 using our MLE method. Assume that the values in the data set should be truncated below 250. Then estimate the cost per payment with a deductible of 500. So just to start off, below we see our data set, and the first thing we want to do is take a look at this data set and truncate our values. So anything below 250 will be ignored, and all of the values above 250 are going to be lowered by that amount. So let's start writing our new data set. So as we're writing our new data set, we notice that 5 of the values listed are below 250. So instead of going into our updated problem with 20 values, we're only going to have 15 in our set. So to go back to the question, the first thing that they want us to do is to estimate the value of alpha using the MLE method. And we know that to start this process, we need to set up a likelihood function. And that function we know is the product of our 15 observations times our PDF. And if we think about the Pareto distribution and look at our notes, we have that our PDF is going to be alpha times our theta of 700 to the alpha power, all divided by 700 plus our individual observations, and that quantity is to the alpha plus 1 power. So our second step, as we mentioned in the beginning of the video, is to now take the natural log of this function in order to change the product to a sum. So we're going to set up our log likelihood function. And for that, we have 15 natural log of alpha plus 15 alpha natural log of 700, and that completes our numerator. And then we're going to work on our denominator, so we'll subtract alpha plus 1 times the natural log of 700 plus xj, and this quantity is going to represent all of our individual observations. So it's going to act like a sum over our 15 observations, beginning with our first. And when we go ahead and simplify this equation, we're first going to, again, just bring down our 15 natural log of alpha. And we can simplify the coefficient of 15 times the natural log of 700 to get 98.2662 alpha, subtracting now our alpha plus 1 times the sum of natural log of 700 plus xj for each of our observations. So the first will be natural log of 700 plus 275, because that's our first observation. and we'll add our next one, so natural log of 700 plus 115. And we'll do that for all of our 15 observations up until our last one of natural log of 700 plus 7,006. And we can simplify this even further to get 15 natural log of alpha plus 98.2662 alpha minus, now we'll add together the coefficient to get 109.4284 times the quantity of alpha plus 1. And at this point, we're ready to take our derivative because our equation is much cleaner. So when we take the derivative with respect to alpha, we get 15 over alpha plus our coefficient of 98.2662 minus our other coefficient of 109.4284. And if we just simplify this, we have 15 over alpha minus 11.1622, and we can go ahead and set that equal to 0 to solve for our estimate of alpha as 1.3438. So we've completed the first part of this problem, which was getting to our MLE estimate of alpha. So now moving on to the second part of the problem, we're asked to estimate the cost per payment with a deductible of $500. So essentially the deductible was raised by $250 compared to our last data set because we had already truncated those numbers by $250. So we are imposing a new deductible on our truncated data of $250. And in order to find this expected cost per payment, we do have a formula for it when we're using a deductible. So let's go ahead and write the formula, which is the expectation of X minus the expectation of X with a deductible, in this case of 250. And that quantity is going to be divided by 1 minus the CDF of 250, again our deductible. So we've set up the formula and we can really plug in all of the values using this Pareto notes that we have because we do have the expectations and everything we'll need for the formula. And when we do that, we can start with the expectation of X, which is just our theta value of 700 divided by our alpha of 1.3438, which we found in the last step, minus 1. And now we're going to subtract the expectation of X with the deductible of 250, which by following the Pareto notes formula, we have, again, our theta of 700 over alpha minus 1 times the quantity of 1 minus 700 over our deductible value of 250 plus 700, and this whole quantity is going to be raised to the alpha minus 1 power. So at this point we've set up our numerator and we can go ahead and move on to our denominator, which is just 1 minus the CDF of 250, which is in itself 1 minus theta of 700 over our deductible 250 plus 700, all raised to the alpha power. So we have all of our values filled in and we can just simplify by plugging the entire quantity into our calculator, and we get a value for the numerator of 1,832.9803. And then moving on to our denominator, we get a value of 0.6634. And when we divide this value, we come up with our answer of 2,763.017. And this is our final answer for the expected cost per payment. In summary, we were able to come up with an MLE estimator for the Pareto distribution, as well as come up with the expected cost per payment for our example. And that is the end of our video on continuous maximum likelihood estimation. Thanks for watching.